Yeah, so there's a lot of other stuff in here that all those gray ones you probably can't see. But this Usain rate work and this rate of change in moments worksheet, I'm going to pass out a copy of the worksheet to you. It's just kind of jotting down a bunch of numbers. It's nothing that is better computerized for any reason. But the rate work graphing calculator file, GCF, that is what we're going to be using today to get the results that we're going to put on the worksheet in just a little bit. But as I said, let's get to, let's see, where we were last time. All right. Ooh. All right. So we were looking at Usain Bolt because he teaches us a lot about calculus. And we talked about one question that was kind of like this yesterday. This is some different numbers, slight variations on what's asked. But suppose that, again, we're going to use this function f to be the name of the function that relates time since the race started and distance from the starting line. So time in seconds is x, the independent variable, and distance from the starting line is the dependent variable measured in meters. And so what this says is it's also essentially linear. On the previous screen it was right around, what, 0.25 seconds or something like that? I don't quite remember anymore. Maybe it was around 3 seconds. Between 0.395 and 0.415 seconds. So this is a zoomed in section of the graph that shows everything between x equals 0.395 and x equals 0.415. It shows a little bit extra on either side. There's 0.415 that goes past that a bit, but the graph goes off the top of the page, that's all. So it says Usain's speed is 3.07 meters per second, and his distance from the start is 0.702 meters. So answer numbers 1 through 7, if we imagine x varying from time 0.4 seconds to time 0.408 seconds, which there's a lot of numbers in that. But yeah, so there's two x values given, which are the left to right intervals that we see here, essentially, the portion of that graph. So this part of the graph here, the one on the left, shows between time 0 and time 0.5. The one on the right shows, well, just very close to 0.4 seconds, 0.4-ish, a little bit less, a little bit more. So at time, let me pause this. At time x equals 0.4 seconds, that's what this end of this little triangle that's growing is. So at time x equals 0.4 seconds, his speed is 3.07 meters per second. How would you know that? Like, what would you be looking at in this graph to know that? Is that an x coordinate? Is it a y coordinate? Is it something else? If it says his speed is 3.07 meters per second, any thoughts? I said there's a lot of numbers in here. We should probably know where they're coming from. So that one isn't simply shown in the graph. It's not one of the x coordinates, not one of the y coordinates, because this is seconds, right? This is seconds along the bottom. And this is distance from the starting line, meters along the vertical axis. If we're trying to find meters per second, you can see from the units on that, that's a ratio or a rate. So it's a ratio of meters per second. So if I say that someone's running at 3.07 meters per second, thinking back to what we talked about a while ago, like, oh, well, it means for every second they're going to go an extra 3.07 meters. So, well, that's if you're going at a constant speed, or at 2 seconds you could go 6.14 meters, or in a half a second you could go, I don't know, 1.535 meters. If you can divide by something else, go for it. But this speed, that's the ratio of meters traveled to seconds that it took to travel that far. And so if I'm looking at this graph, where I could maybe see that is the relative sizes of these kind of triangle parts, these two pieces that form this triangular shape with our graph. So our graph is going up. This, again, doesn't mean that Usain Bolt is going up. This means that his distance is increasing as he goes across. Well, he is literally going across the track. Well, I guess along the track. As x increases, as time increases, his distances from the starting line are increasing. But for this much change, that small amount of change, and I'll move my arrow off of there so that'll go away. For a small amount of change in time, dx, there's a corresponding small amount of time in the y variable. Now it says df there. Sometimes you'll see that notation. And it's like, well, f is the function. It's really dy that we'd be talking about here. That's more standard notation. This is just a pre-made graph that was someplace else. But the horizontal change and the vertical change in this picture represent a small amount of time going by and the small amount of distance that corresponds, or the small amount of distance that he ran during that small amount of time. And if we compare the ratios of those, since the units on this df, or this vertical change in the graph, would be a small number of meters and a small amount of time in seconds, I can get meters per second for that interval. Since it looks like a straight line, we're going to play around with a GC file where we can actually see numbers and do computations, and we're going to write a computation to show us what that ratio is. Instead of just saying it looks like a line, we're going to do some computations and see that it's extremely close to a line, and depending on how close we zoom in to something that's a polynomial function is what we're looking at. Remember, a fifth degree polynomial. Depending on how close we zoom in, it is closer to being precisely linear or farther from being close to linear. But, you know, to the naked eye at least, it seems reasonable to say that, oh yeah, I should be able to state a rate of change, which in this case is a speed for him. Over this interval, it's not really changing a lot. He's not getting faster and faster. Like if you look at the graph on the left there, that curvature we talked about last time, say, oh, well, at the beginning it's less steep, and then later on it's more steep, indicating slower and faster because of fewer and more meters per increment in time that goes by, however big those increments are. All right, so again, back to the numbers in the question, a whole lot of them. We're looking at a small interval of time, right around 0.4 seconds in the race, but we've got some on either side so that we can look at 0.4 seconds in the middle of this graph, not precisely middle left to right, but amid the graph. It's not right on the edge. And then let time vary a little bit past that. We could have even gone backward a little bit and varied a little bit the other direction to see what happened as opposed to what's about to happen. But as we let time vary a little bit, we'll see that the distance varies a little bit, and we can measure that speed over this small interval then, and even, you know, just letting this, it could be, you know, it looks like the same steepness all along, and this is all within that, oh, let's see, well, we're starting at 0.4 and not even getting to 0.415, so 15 thousandths of a second. He's probably not changing speed a whole lot, but it's about 3.07 meters per second. And at the beginning of this, at time 0.4, the spot at the left end of that triangle, the distance from the starting line, y-coordinate in this graph, is this 0.702. So we have all those numbers at the top. A bunch of them are seen directly in the graph. That 3.07 is the only one that's a computation from the graph, or that isn't just a read a coordinate point. But look at these questions 1 through 7. Imagine, I'm going to set this to play again. Imagine x varying from time 0.4 up to 0.408 seconds, which is what's going on in the picture. And think about the symbols that represent these, if there is one, and the values for each of these 7 items in the list. See if you can determine what would be a way to express these, or what value corresponds to this situation. And again, it's not the whole window 0.395 up to 0.415, it's just 0.4 to 0.408, which is up to about there. I don't know, I can't quite see when this slider could, a little bit past that. I think it's about there. Oops, sorry. So that's the first one we talked about last time. There isn't a symbol for moment, but see if you can come up with a way to describe the value or values for each of these and the symbol for everything but the first one. So this is at the maximum. As I let dx vary from 4, or x vary from 0.4 to 0.408, you can see this dx, or the variation in x, that's at its maximum extent right there for the question that we're talking about. So think about these. I'll give you a couple minutes. Maybe jot them down, maybe just think about them, maybe ask your neighbor if you agree. And not all of these are just a simple value that's already listed. You might have to do a computation. So for the first one, this moment. Moment is one of the most vague sort of statements. And there's a lot of different good answers for this one that we could use. Like, what moment are we trying to use? There's a lot of not correct answers, but there's a lot of answers that we could use for this. The idea with this moment in question is we want to be able to pick, it's an interval. We want to be able to pick an interval in the independent variable. So some interval of x that includes all the stuff that we're trying to talk about. So this moment can't just be a single x value. And I don't want it to be the moment of x equals 0.4. It has to be some interval of values that includes 0.4 and, well, in this case, all the other numbers that we were using. So it needs to be at least from 0.4 to 0.408. What was the other number? Yeah, 0.408. But you can use anything that includes that. So this whole graph on the right, that whole left to right, that could be your moment. Just whatever window you're using to view this change where it seems to be approximately linear. So you could say 0.395 to 0.415, something like that. And just all of this is occurring within that small time frame. As long as your moment includes all of what we were asking about here, so that you can be just describing what happens within that moment and not something that happens later, then that's an okay answer. So something like 0.395 through 0.415, interval notation there, I just did that for brevity's sake. That'll fit in there. You will see some questions in the homework where it asks you to write things in interval notation. You can't use interval notation to define spots in GC, but generally in math you can. GC just uses other notation. They will use the less than, greater than sort of interval inequality notation. All right, so what's the rate of change according to this question? We don't have a GC file that we're using on this right now, actually. You probably could actually pull this up. But what's the rate of change that we're using in this moment, or that's given that corresponds to this moment? Yeah, 3.07 meters per second. What's the symbol that we use for a rate of change that's constant? M, right? Yeah, so we can use M, or we could use dy dx, dy over dx, that ratio of small changes. In the graph down below would be df over dx. That'd be okay for this question since it was labeled that way, but probably not a preferred answer. That's slightly, it's notation that's used because it's understood to really be df of x dx, but that just gets confusing with all the x's in there. What about the initial value of x? We usually use xi for that, but what's the value that we're using for imagine x varying from, like this last sentence here? Yeah, 0.40, 0.4, yeah, up through x final, 0.408. What's the differential in x then? Yeah, it's that 0.008, which the symbol for differential in x, that's that just dx on its own. But literally that's just corresponding to that x final minus x initial, or how far are we letting x vary. And for this last sentence here, answer 1 through 7 below, if we imagine x varying from 0.4 seconds up to time 0.408 seconds. So that's 8 thousandths of a second, 0.008 seconds. Differential in y, symbol is, yeah, just dy. Or if you wanted to, you can write a computation for it, mdx, because dy equals mdx when we've got a constant rate of change like we do. And what is dy, the change in his distance from the starting line, or df, if you wanted to use that notation, for this interval within our moment that's pictured? Well, we have to do that computation. We would need to do m dx, right? So we could write it as a multiplication problem, but we'd need, for, let's see, 3.07 meters per second for 8 thousandths of a second. So it's not going to be a lot of meters, but this 3.07 meters per second, it's a constant rate of change, not forever, but within a small moment of time, and certainly within this 8 thousandths of a second, it seems like a reasonable estimate based on, well, what we were told. Now, how we could calculate that is by knowing dy to start with, we could calculate that rate. But if we know the rate, we can also calculate dy. So we can, if you know any 2 out of 3, dy, m, dx, if you know any 2 out of the 3, you can calculate the corresponding third one. It is just an algebra equation. Normally, dx is not the unknown quantity in these sorts of problems because x is independent and we let it vary. But lots of times we're wondering, what's the rate of change? How fast is something happening, maybe, if it's something related to time? Or what has happened? How much has happened because of this known rate? Those two things are usually the pieces of that dy equals mdx, the dy and the m. Those are usually the two pieces that we're looking for, whether it's just for a single moment or collecting together a whole bunch of consecutive moments and looking at changes within each of those and finding rates that correspond to those. Because for Usain here, he clearly is going slower and then faster, but as long as we use some slower rates to figure out what happened at the beginning and faster ones later, we could reconstruct his whole race. Or, since we know his whole race, we could find from that his rates at any moments in time during it, using the data that we have. So we could go either direction. In this case, we're going to start from knowing distances and finding rates, but we could go the other direction also if we had different data. So in any case, a differential in y would be 3.07 times 0.008. That's where this number comes from. But again, this represents here in 0.02456, so 2.456 centimeters in that 8 thousandths of a second. All right, Usain's initial distance from the start. So his initial distance from the start in this moment, not overall in the race, overall in the race would be 0, would be his distance from the start, or that y initial at time 0.4. And since this function is called f, we could also refer to it as f of 0.4, f of 0.4. But we also know what that value is, because it says it up above, right? Let's see, at time 0.4 seconds, his distance is 0.702 meters. So in that little picture there, if that's 4/10 of a second after the start, there he is, not even quite 1 meter from the start. Foot maybe still partially in the blocks, but final distance from the start. Why final? How can we find that? Meaning not Y final as in 100 meters he finished the race, but Y final for this situation. Yeah, add the differential. So we had his initial distance from the start at the beginning of the moment. At this point in time, he's 0.702 meters from the start. As a small amount of time went on, he traveled this 0.02456 extra meters. So his new distance from the start is his old distance plus the amount he traveled during this small interval, during this 0.008 seconds. So symbol-wise, there's a lot of different ways we could write that. We've got his initial position plus his extra, so we could just add together these two. But in symbols, we could say, well, f of 0.04 plus dy, y initial plus mdx. I could just call it y final, but if I want to explain, well, how on earth did I get y final? We could use some of those symbols that we used earlier on, because we were just looking for his initial distance from the starting line plus what happened during this 8,000th of a second. So, like I said, there's a lot of different ways we could do this. You could even just use, oh, it's f of 0.408, because in reality, we actually are going to have a value for that we can find on our graph that we'll look at in a moment. But here's what that sum is, 0.72656, just by adding the previous two answers. But that's y initial plus mdx, the starting distance, the starting position, I'll call it, plus the change during the next 0.8 of a second, plus the extra distance he ran during the next 8,000ths of a second, rather. So when we're working from, and this is what we're going to be actually focusing our time on starting next week, when we're focusing on what if I know how fast something's changing? In this case, what if I know how fast Usain Bolt's running at any point in time? How can I figure out how far he runs in the next however long? Well, since he's probably not running one constant pace all of the time, I'll break it up into little tiny chunks and look at his speeds during little tiny chunks of time and pretend or assume that it's almost constant, so my answer is going to be close enough, it's going to be a good estimate, and I can reconstruct his rate from that. Now, what we're actually going to do today is start from the GC file, which is posted here. It says Usain rate work. And let's see. If you open that up, let me make mine a little zoomier. There we go. Now that I have a screen that actually fits, a projector that fits what's going on here. It has some stuff in it, and as you can see, there's some things that are written and there's some equation lines. So the nice thing about GC is, kind of like with computer programs, you can like have lines that aren't really doing anything, they're just for text and descriptions. That's what these are. These are non-computation lines, just to kind of describe what's going on. So I've got this t is the elapsed time since the start of the race, f of t is Usain's distance from the start in meters, and here's that 5th degree polynomial that I showed you in class Tuesday. So first task, right now you should have a blank graph down below. Type something in this line where right now you either see a question mark or an error message. It says nothing to graph, depending on where you've clicked on this. But type something on that blue line to make it graph function f of t that's shown above, where, well, we don't really want it, we can't really use t because t, GC wouldn't understand. GC understands y's and x's as graphs. But I want you to type something simple using function notation to display the graph of this function with x being the time in seconds along the horizontal axis and y being that distance from the start. So the graph that we looked at before. But make it just display 0 to 9.58 seconds, because that's when he finished his 100 meters. That's why it's such a weird number. And if you're done with that, I just realized there's some stuff right below that. Slightly off to the side of the screen. It says control the current value of x. There's nothing in between this next stuff. There's nothing to do in here. These are pre-typed formulas. Task 2, the next thing to do is down here in boldface. So if you've got your graph showing and can kind of zoom it around to look like what we saw yesterday, like show the 0 to 9.58 seconds for sure left to right, but make sure you've also got the whole 100 meters top to bottom. So use the zoom features that are in the bottom left, and you can zoom in one axis, or if you can see the whole graph, you can do the shift click and draw a box around what you want to zoom in on. So while you're working on that, I'm going to wander around a little bit, and if you're having difficulty with GC, let me know. If you don't have a laptop, maybe find somebody that does to sit by, so you can look on and see what's going on and practice with GC. If you've got your graph from 0 to 9.58, it doesn't have to move. Yesterday I had a moving one. We'll talk about that later. Remember, if your graph just seems in a weird spot, if you can find the X and Y axes, you can also just click on them and drag the graph around by those. What we're going to do is zoom in, kind of like was on that last slide of the presentation I just had up. We're going to zoom in around, I just use C so that it doesn't try to graph anything, a current value of 3. We're going to zoom in around x equals 3 and investigate some stuff. There's some extra programming that's tossed in this down at the bottom that you don't have to mess with. But when we look at the graph and zoom in around 3, you'll see some extra things if you're zoomed in close enough. But first task, if I want to graph this function f in terms of the x and y axis, what do I need to type on this command line here? Yep, y equals f of x. And make sure you get the control 9 parentheses if you're not getting a graph, if it's not the graph of a curve like we were expecting. What do I need to do then to get it to only show 0 through 9.58? Because if I just hit enter right now, I'll have a whole polynomial. Yeah, the domain. So I'm going to hit comma, and then 0 to 9.58. If you use less thans or less than or equal tos, it'll look exactly the same. So if you're struggling to get the or equal tos or can't remember which buttons to hit, don't worry about it. It'll look the same. So I'm just going to do it the quick way. But x between 0 and 9.58. And then I'm going to hit graph and try to get this zoomed in like I hope you did. So this, again, this graph window, you can make it more or less of your screen. Just drag it by clicking on it, and it should give you this little two-sided arrow so you can move it around. And if yours is already set like this, then great, you can see the graph. But what we want to do, and I had this kind of expanded so you could see the whole thing at once, but if you're at these instructions here, control the current value of x equals c and the value of dx. There's some other stuff we're going to type in there so that a value will be shown for m, and that m is going to be exactly what I hope you think m is going to be. It'll be a rate. Dx should also sound familiar. We're going to see what happens for various values of dx, but for right now, just leave this arrow here, or this slider to the right where it says 0.1. It'll make it easier to see what we're going to do. But if you do have it at 0.1 and you're zoomed out, you might even see a little something happening down here at x equals 3 on the graph. On mine, you probably can't see it, but on the screen in front of your face, if you play around with this, when you have x equal to 0.1, you might be able to see a little blob that's sticking out of the graph suddenly. So that's right around x equals 3, this current value, c equals 3. So what I'm going to do is hit the shift button, and then click to draw a rectangle around this. So just drag a rectangle around that. And here's a close-up of what that little blob was. So, all right. So I've got, kind of like in the picture we were just looking at, I've got this arrow that starts at, well, nothing. If I move it a little bit past 0, I can finally start to see this forming, and I can make this arrow go as long as 0.1 units. And this is connected to this thing. It says slider. This is how you can make sliders out of things, but this is dx. And then, so this is representing dx. That seems reasonable. Dx is a small amount of change in the x coordinate. So in this case, x was our distance from the start. All right, so let's get down to some of the other things that this said to do. Plot the points for the current value of time, so at x equals c. So just literally use the letter c, not 3. So what we're doing is we're using a parameter so that we can change what happens in the graph easily by changing the value of c up above. So if I want to plot a point at c, which right now happens to be 3, because it says so right here, c equals 3. If I put in this coordinate point, c, that's going to know I'm talking about 3 right now. What's the y coordinate that would automatically go with an x coordinate or input of c? How could I express that, or how could I represent that? F of c. I don't have to come up with a number for it, and I don't have to write out that 5th degree polynomial with c's in it. I can just write, oh, f of c. And if I hit enter, you can maybe see now there's a dot right at the beginning of that. So what I did want to show you is here, I'm going to scoot my graph down a little bit so I can have more of this computation available. So if I were to go up and change this to c equals 3.1, now the point moves around. So I can just change the value of my parameter c by changing this stuff up here. And I can still change this arrow, but everything that's coordinated to go around with c, and that arrow is what the mystery, like, extra stuff programmed. If you scroll all the way down to the bottom of the text part up above, you'll see some weird stuff in purple. It's just this little arrow. It's nothing too complex, but I didn't want you to program that in. So it says plot the points for the current value of time at x equals c, and for a value of time that's dx later. Well, dx is something that I want to be able to control with this, so I just want to refer to it as dx. So if I want to put in a coordinate point for that, the x coordinate shouldn't be c plus a specific number, but it should be c plus dx. Now let's see. Yeah, dx was already defined, so you can just type it as dx. I don't know if you talked about this as a part of, or if you remember from your intro GC expression, but if you want to have more than a single letter to represent something, you have to tell the computer that. Otherwise, it thinks you're doing multiplication when you write multiple symbols together. So it's, if you've done computer programming, it's like defining a string. You just put a little slash in front of it, and then you can type what you want, and it'll know that you're making up, you want all of the letters to go together, and then you can define it. But dx is already defined up above, so you don't have to define it here. You can just type it, and it's like, oh, this is the dx that you mentioned earlier. So that's the x coordinate. And I want the corresponding y coordinate to also be a spot on the graph. These are, so I'll have a second gray dot. If I want the y coordinate that goes with this x coordinate, it should just be f of that, right? So f of c plus dx. And if you hit enter, you should see a second gray dot. So now we have a graph that looks like, this is starting to look a bit like what we had up on the presentation earlier, right? So all of this stuff is just done in GC. It's not magic. But because we have those parameters in there, and this one is, this dx is defined to be a slider because I have those symbols in there. So c, I'm just leaving to have one value at a time, and then I let dx vary. So I have one parameter and one variable. I'll just put this dx at its largest, but I could change c to be something else too. Like what if c was 3.1? just to pick something that also be in this window. Everything moves along with it and still does the same. Now we've got one missing part up here. I'm going to put this back to just plain old 3. This M says no equation to graph. Okay, so what is M about? Task 3 says to write a formula that computes M, the rate of change of y with respect to x, for a short interval of length dx starting where x equals c. Or in other words, compute M for this interval. Here's x equals c. We defined c to be 3 up above, but here's a specific picture. Here's x equals c. Here's a point that's dx later. I want to find M, that constant rate of change, or approximate constant rate of change at least, over that interval. So, see if you can write a formula to calculate rate of change for this interval. Since it's approximately a line, this looks approximately like algebra 1, just messier. Rate of change of distance with respect to time in our context, or y with respect to x in general, meaning dy over dx, that ratio. So what are we going to need? Maybe first, it's a ratio. What's going to be in the numerator? Yeah, our dy. So here are two generic coordinate points, where I can change c and I can change dx to make them any 2 points. But if I want to use, in general, calculate a slope between whatever those 2 points happen to be, I'll just use those symbols, right? So f of, to get, yeah, c plus dx, so I get y final. Yeah, so y final minus y initial, f of c plus dx minus f of c. And then just in order to get this all to be divided, if you select all of it and then hit divide, it puts a line under it so it looks like a fraction, which is fun. Instead of like having, you don't have to use parentheses. Yeah. So this can save you a little bit of time. You can do this just the way you would on an old TI calculator, put parentheses around the whole thing to be able to divide a long expression all by something. Now our denominator, we can do the same thing. C plus dx minus c. Notice that simplifies a bit. If you do that x final minus x initial, what does it simplify to? Dx, which should seem reasonable, like, oh, okay. dy over dx. I don't want to just write the symbol dy, but by the time I'm done simplifying my denominator, it's just the symbol dx. So I've got dy divided by dx, so this differential in y, a small amount of distance traveled, divided by a small amount of time that passed while that distance was traveled. So that this, now we've defined what m is. This m is going to be a set of numerical values. For any value of c and any value of dx, this is going to be something that we can compute. As long as dx isn't 0, right? Dx equals 0 is bad. Denominators can't be 0. But if we scroll back up to these computations, notice there's a number for m here. That's just giving us the value of the formula that we wrote. So I can see now with c equals 3 and dx equals 0.1, meaning, I'll just, oops, move this out of the way. See the interesting part up here. If we're looking at Usain Bolt in a smallish moment, 3 seconds into the race. Now this is 1/10 of a second as opposed to what we were looking at before, 8,000ths of a second, so it's a larger moment. But just eyeballing this graph looks close to linear. There's not a huge curve or point in the middle of it, so this, I could say that this is approximately linear at least. and I can say that his speed during this moment is approximately 10.828, just number of significant figures. You might have more digits on yours depending on your settings, of about 10.828 meters per second. What I was just talking about with the settings, let's see, where is it? Document settings is under the file menu. Mine is set to 6, so since this came out to only 5 digits, I know it's done all of the computing it can do. So just realize if you're getting decimal answers for these computations, a lot of times they are rounded off or they're just approximate. In this case, since it was 6 significant digits and there's only 5 numbers, oh, well, this must be precisely. It is a polynomial, and we have a nice round number of 3 used as the x input and 3.1 used as another input. Those are going to be terminating decimals even raised to the 5th power. They're just kind of long, but this whole ratio came out to be exactly 10.828. That's the slope between these 2 points if it's exactly a straight line. Now I know it's not really a straight line, right? It's a polynomial function. Those are curvy. They're not straight lines, but they're fairly straight. If I play around with this slider, I can see how close it is to being straight, or I can see, well, what if I don't look at a whole 1/10 of a second later? What if I look at, let's see, 100th of a second, if I can get it to be 0.01. 100th of a second. I've got 10.7825. Well, that's pretty close. It was 10.828 before. This isn't a whole lot different. But, I mean, I could get smaller. It's going to be, if I go to 0, it doesn't give me a value. Notice if I make dx 0, I don't get a value for m. That's good because that would be a fraction with denominator 0. But if it's 1,000th of a second, I get this 10.7778. Now that's likely rounded off from 10.7 repeating, seems like. But if you can see, if I move away from 3 seconds into the race, anywhere from 1,000th of a second up to 1/10 of a second, the speeds that are computed, as if it were exactly the same speed all the time, don't vary too much. So it's not exactly a straight line, but 10.777 up through 10.83, speed-wise, those are fairly similar speeds, agreed. They don't vary a whole lot. Now, if I wanted to be more precise about his speed, I could talk about, well, let's not go a whole 1/10 of a second at a time, because clearly this graph, even though I can't see it, is apparently getting steeper out here, which that should maybe make sense. Think about polynomials. This is going up. Polynomial going up, like, oh yeah, this is on one of those parts where it's getting steeper and steeper. It's just I'm zoomed in so far looking at a small section, it's hard to tell that. If you remember the graph at the beginning though, it started from this 0, 0 and was curving upward and just kind of seemed to go upward forever. So maybe that's true all along. What I'd like you to do, and this is what the worksheet is, we just went through the line equivalent to, here, let me pass this out first and we'll talk about it when you have it in front of you. Pass this in the aisle. What we just did was the line across from C, insert value of x equals 3. We went through, and we've already done the hard part. We've done all the pre-programming this to make different values. So let me see if I can find I'll just pull this up from Canvas. Let's see, Usain Bolt, rate of change worksheet. So what we just did is when dx is 0.1, that was that 10.828 number. With dx is 0.01, I forget what that was, 10.79 something. And with dx is 10.001, meaning looking from time 3 to time 3.001 seconds, we have this 10.7 repeating sort of thing. So using that GC file, what I'd like you to do is go back and do the rest of these. Maybe, let's see, how many rows do we have? 1, 2, 3, 4, 5, 6, 7 rows. 1, 2, 3, 4, 5, 6, 7. Well, I've got 8 of these. So how about everybody do 0.25. If you're in the first row, also do 0.5. If you're in the second row, also do 1.0. If you're in the third row, also do 1.5. If you're in the fourth row, also do 2.0. We already did 3, so nobody gets to do that again. If you're in the fifth row, do 5. If you're in the sixth row, do 7. And if you're in the back row, do 9. And so what I mean by this is everybody's going to do 0.25 and one additional row here. So in our file, if they're doing 3, which is what we just did, make C equal to 3. And then I'll start off 0.25 to get you started on this. Then look at, see if you can slide this slider to get to 0.01, 0.001, and 0.1. Those the first one and the last one are the easiest, like 0.001, 1,000th of a second. 1/100th of a second is kind of hard to scroll exactly to, and 1/10th of a second is at the end. Now, what I would like you to do also, it's not necessary to get the computations, but it's much more interesting if you do. We're all going to do 0.25. Now, this graph does not show anything because we are not zoomed into 0.25. We are someplace else. So whatever number you're doing besides 0.25, zoom out until you can find it someplace so you can see the little purple arrow things. And so for 0.25, we have a graph that looks quite a bit different from the last one, but this is 1/4 of a second into the race. So look at the set of 3 values for M that you get at the 3 different values of dx. And we're going to talk about the patterns in those in a minute. So take a few minutes. Everybody use this 0.25, and then you're all assigned a different number. So you all in the front row are on 0.5, 1, 1.5, 2, 5, 7, and 9. I'm going to mute this for a second. So again, we're looking at distances traveled over varying amounts of time at different moments during this race. So during that 0.25 current time, at 1/4 of a second into the race, we had these extremely small, comparatively speaking, M values, rate of change values. So if we go all the way from 1/4 of a second to 35/100ths of a second, 0.25 to 0.35, looking at that interval, if I imagine x changing, so over that interval, if I use the entire interval, I get this 2.42 meters per second. If I'm at 1/100th of a second, 2.13, or back to 1,000th of a second, 2.1. So this one changes more than when we're around 3. Changes from 2.11, 2.13, 2.42. So that's 3/10ths of a meter per second faster if I look at the whole tenth of a second versus a thousandth of a second. So maybe a tenth of a second is way too long to use for estimating a constant speed, or over this, I mean, this is pixelated because of it's relatively horizontal, but not quite. So this looks like the whole bunch of jagged horizontal lines, this blue curve when we're zoomed in like this. But here should be some numbers you get looking at this. So 0.25, we just looked at those numbers, and we did 3 together already. So I know I get more accuracy, my speed, if I use a smaller interval. That should be more accurate to like estimating the left end of the interval if I go less far away from it. So these are probably better estimates of the speeds at time x equals 0.25 time x equals 0.5. But what does that mean to have a speed at a point in time? That doesn't make, like, if you're at one point in time, then and not going forward, then nothing is changing anyway. So all of these mean something. There's not like this is a wrong answer or this is a bad answer. They're just telling us different things. Now, in terms of how we associate, like if I wanted to write a function that assigns a speed value to every point in time during its race, like, well, there has to be a single number for 0.25 seconds. I don't want to use all of these. So I'd pick something probably that's closer to this 2.11. Maybe I'd even go to a 10,000th of a second or 100,000th of a second to get some results that are, you know, like more accurate. But if I wanted speeds for every moment during the race, if I make smaller moments, smaller intervals over which I let this dx vary, then I'd have to have a lot more moments. So we were looking at kind of like smallish sizes of dx, letting dx vary, and I just picked a few points in time during the race. But thinking about the patterns of these numbers, looking over this tenth of a second here at a quarter of a second into the race, relative size-wise, that's a relatively large amount of variation in time. But we get this large number for speed as compared to if I look closer to, at a moment that's much closer in to 0.25 seconds, I get this speed 2.11 meters per second. If I look farther away, use 0.25 to 0.35, I get a larger speed. What does that indicate about how he's running during this time? If I'm looking close to time 0.25 and I get this speed, and if I look farther away, like over a larger interval starting at 0.25, I get a larger number. Yeah, it indicates he's speeding, and you can see that it isn't like speed up, slow down by looking at the, you know, the pattern of numbers here, kind of, but really it's a polynomial. We know it's not changing concavity, curving up versus curving down over and over again in that tenth of a second. So just using some math facts that you have in the back of your brain. It is not just like we picked some numbers that make it seem like something's happening. He's actually speeding up. This is the speed. These are all speeds that we measured starting at the same time, but we just used as an end point to the interval things that are either closer or farther away. So looking at this pattern of numbers here, it's kind of the same throughout, although at the beginning there's a large difference, 0.3 meters per second, between using a small interval and a large interval. The one that we did together, 0.1 meters per second, or less than that actually, 0.05 meters per second, between using a smaller interval and a larger interval. So some of these are closer together and some of them are farther apart. These being pretty close together, that would probably indicate he is traveling at a pretty constant rate during this time, or right around 3 seconds into the race, whether I look at a very small interval or a not quite so small interval. The difference in my computations is 0.05 meters per second. It's not a huge difference in speed now in terms of if he was running at 0.05 meters per second faster than the person next to him, then yes, over a 10-second race, he's going to definitely win. But in the scope of measuring speed, 0.05 meters per second, maybe not a huge difference. At 5 seconds into the race, the difference is even smaller, and some of these are even identical results to 2 decimal places. So 11.9, 11.9, 11.91. And again, the leftmost is when we're using the largest interval. Look at the last row. And those of you in the last row might have noticed that what we just found was different from what you found. This is at 9 seconds into the race. So 9 through 9.001 seconds. This is the speed calculated. If I go out a little farther, I get something that's slightly slower. If I go out farther again, I get something that, again, is slower. What does that mean? Slowing down. Yeah, this is right at the end of the race. Now, the race was 9.58 seconds, but if you remember the video from the other day, he was winning by, well, in a sprint race, by quite a ways. Sprint races are often, you can like hardly even tell who won, but he was like a couple, like he was a step in front of everybody. They were like well behind him. So yeah, he's probably slowing down like, yeah, I got this one. End of the race before he hit the finish line, because this is at 9 seconds. So this is half a second before it was over. He was already slowing down. So in any case, and he still got a world record. In any case, the patterns in these are something that can be useful to know about, instead of just saying, well, what is the actual exact speed at a point and being concerned like, oh, this is just an estimate. If you talk about a speed at a point in time, that can't really exist, because a speed would have to indicate that there's change going on. So a speed is only useful if you apply it to an interval of time or an interval of some independent variable changing values. That's how it's useful, if you allow something to change, not if you freeze it in time. But also looking at what the patterns are, what happens if I calculate this differently, can tell you about what you're finding. It can tell you that, oh, well, during the first part of the race, he was speeding up, that makes sense, and at the very end, he was slowing down. Well, that's probably something you could have guessed without doing computations, but it's nice that you can actually see this in numbers as well. So what I did want you to not forget, though, that all of this is related to, let's see, where did it go? This. All this is related to our graph that we had. And let's see if I can get this way, that way. All right, zoom out a ways here so I can see my whole graph. There we go. This way. There we go. All this is related to this graph here, and you can see the changes happening. Now, if you actually wanted to have the graph do what I had in class the other day, sorry, I was trying to move this here. If I wanted this to generate like a cross as time goes on, instead of worrying about changing over a moment, if I wanted to see what happens as time goes on to him running, we could change this to have a slider, either a slider that we create ourselves, or just in this row here, I'm going to let x go from 0 through n, and now I have my n slider down at the bottom, and I'm going to let n take on a highest value of 9.58. So now I can hit play. Now I'm going to have this little, when I'm doing this, it's useful for looking at the big picture, showing the graph generating over time, as opposed to just looking at what we were doing before, just looking at over any individual interval. So I could have used, I just created that separate slider dx, so that A, it could be named dx, but B, so that we could just play with it manually and not worry about just like, oh, this is playing over and over and over again. But this picture, we can see like, let me see if I can, let me stop it. You can drag this manually too. So again, at the beginning, it's kind of hard to see from this level of zooming, going pretty slow, those lower numbers of speeds, and then faster and faster and faster. And the fastest speeds seem to be somewhere right in the, what, 7 to 8 second range? Is that where it was? I guess it was up to, yeah, this 7 was the last number that we had. Now, if we did 8, I'm not sure whether it'd be slightly higher or slightly lower, or just about the same. But the fastest speeds we had were 12 point something meters per second. Go back to this one. So in this, like, around 7 seconds, this is the fastest. And then he actually starts to slow down at the tail end, which if you look closely at this end, maybe you can see, oh yeah, that seems like it's starting to curve down. It's a polynomial graph. It was going uphill, but maybe it's starting to head towards the top. Now, this is the only part of the polynomial that was useful for this situation. The rest of it doesn't apply. It was meant to model his distances, and that's how it was put together in the first place. It wasn't like, oh, Usain Bolt's running, this is the equation we use. No, it was just based on data from the track. But there's one other thing I want to point out, and this is the bottom part of your worksheet. So it says, using a result above with dx equals 0.001, so the ones that I have bold-faced here, the right column. Suppose we wanted to graph a function, and I've named it r sub f of x. So the rate, r for rate, and a subscript of f to be the rate of change of function f, the thing that we graphed before. So if I want to graph the rates, or in other words, draw a graph of what his speeds were, that's a totally different graph from the graph we were just looking at. That's a graph of where he was. If I want to draw a graph of his different speeds, which we didn't calculate his speed at time 0, but at time 0 he better have been going like 0 meters per second, or he's cheating. But by time 0.25, he had a speed that was above 0, and then later he's going faster and faster and faster, and then slower. So if I want to draw a graph where the dependent variable is his speed, so his distance isn't shown in this. If his dependent variable is speed against time, we have a bunch of data points, however many this is. 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 different speeds. We could draw, like, well, I'd say scattered plot, but they're not really scattered. They kind of fall in a pattern also. This would be a graph of his rate of change, and that's what we're going to be focusing on next week, graphs of rate functions and what they mean and how we can recreate what was accomplished from those rates from them. But if we drew this, I have it pre-drawn down here. The red dots are the dots that were in the values that were in the right-hand column. But I drew a thing through it. But here's that at 0.25 seconds. Here's this 2 point something meters per second. At 0.5 seconds, here's the 3 point something meters per second, and so on. By 3 seconds, this is the one we did together. It was at 10 point whatever meters per second, and then a little faster. The fastest speed we got was around 7 times 7 seconds, 12 point something meters per second, and the last speed in the chart that we had was slightly slower. It was, what was it, 11.76? So these aren't evenly spaced coordinate points that we had. We just had an assortment of things. Some of them were spaced the same as other ones from one another, but there's just 9 points. But this graph then could be a graph of his speed, and the connecting of them would indicate, well, what do you think his speed was doing in between the data points we had? So I may just go through, well, it's kind of hard to see, go through approximately 0, and then it has to get up to over 2 in the first quarter of a second. And, well, he has to be speeding up, so it's kind of made a smooth curve that goes through these points. But then this graph, every single coordinate pair on these, including where those red dots are, but also everything in between, represents a pair of values, x comma y, where now x is a point in time and y is how fast he's going in that moment. So what we're going to start working on next week then is, how do I take information like this? Because this is maybe the weirder aspect to it, but the computations are exactly what we did before. How do I take information about rate of change and recreate what happened because of that rate? So how do I start from speeds and figure out distance? If we only used these few points, we probably wouldn't get exactly 100 meters traveled in 9.58 seconds. We'd get something maybe close though, because we do have a lot of data. But we're going to think about what would that process be if I have a bunch of different speeds, not just one speed that I use or one rate that I use for an entire situation. All right, so that's it for today. Thank you for playing along with Usain Bolt. And there is a Canvas quiz that's open as of now. It's open through midnight. You don't have to do it immediately. There's no password. But it's about moment and rate of change in moments and what those mean. Just 2 quick questions. Multiple choice.